Hey, dude, I am so freaking excited. I discovered a new number sequence. That's a bold claim, I know, but I promise you I did. I almost discovered it. I'm almost the first person to find this one. There's somebody who beat me by 4 months, but I discovered this independently, and I'm extremely excited to share this with you all today. If you stick with this video to the end, we'll even prove the most important part of this fact using our new tool called mathematical induction. The beginning of this video is going to be very accessible. Anybody can understand it. But then at the end of the video, at the very end, we'll use the proof technique of mathematical induction. And if you haven't seen the previous episodes yet on induction, it would be helpful to see those first. But otherwise, this video is totally self-contained. So without further ado, here it is. And this is going to be fun, I think. One cool thing about YouTube as a medium is I can invite you to pause the video and try to find the pattern yourself in this. I discovered this number sequence. This is how I actually write it down when I'm practicing this. What's going to happen is I'm going to give, I think, 4 different hints, 4 main hints. And if you want to try to work the problem, you can, or you can resume the video. You can take the next hint, or you can just hang out and be here for the vibes. I'm sure Luna will show up at some point, of course. So anyways, here's the number sequence. I'm going to give you a chance right now to pause if you're with me. Welcome back. Let's continue. Here's the same number sequence again. This time, it's just ever so slightly different. This time, I'm going to give my first hint here. This sequence breaks into groups. And these are the first groups. So pause the video if you want and try to figure out what's special about these groups of numbers. Like how am I coming up with these groups in particular? If you're with me, I'll go ahead and fill in all the other groups. So we got these as well. Oops. There it is. So the last group was incomplete, and then there's the remaining numbers for that last purple group. All right, so another hint is if we write those groups differently, it's going to be a little easier. So if you haven't paused the video, here it is. Let's write out those groups in a triangle fashion, or 1 per every row. So right now, here's another chance. Now that I've written it this way, I wonder if you can spot any interesting mathematical patterns here. I'm going to give it 2 or 3 seconds or so to give you a chance. If not, all right. The first one that I bet a lot of people... I ran this in my live stream earlier today, and it was really cool. People were noticing some patterns that I didn't even notice before. By the way, one thing, I keep forgetting to say this at the beginning of the video. I see in my metrics, 95% of people watching these are not subscribed. If you're enjoying these videos, it would help me a whole bunch if you're enjoying this to go ahead and hit the subscribe button. But only if you're enjoying it. And in any case, whether or not you like it, I'd appreciate feedback in the comments. Let me know what you'd like to see out of this series in general. All right, back with our regular scheduled program. All right, first pattern that I think a lot of people noticed today, every row begins with an odd number. In particular, every row begins with the next odd number. So we could talk of the 11th row, or the 13th row, or the 15th, or the row starting with 15, 17, 19, and that means something very clear and precise, right? Anything else? So that's how every row begins. Do you notice any other interesting patterns here? I'm going to give it a moment. All right. And if you're with me, every row ends with a square number. 1 squared, 2 squared, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, etc. You see the pattern. Those are the squares in that diagonal. Now, how do we build the rest of the triangle? All right. Pause the video if you don't want a hint. Okay, so we can notice those 2 patterns. here's the main one. So here's the last hint. If you want to try to figure out this puzzle on your own, here's your chance. Otherwise, welcome back. Let's do this. I'll show it to you all. All right, how do we get from 3 to 4? What's one way to get from 4 to 4 from 3? You can add 1 to 3. How can we get from 5 to 8? We could add 3, and then from 8 to 9, we could add 1. How do I get from 7 to 12? 5 plus 5 plus 3 plus 1. And then the next one, plus 7 plus 5 plus 3 plus 1. And then the next one, plus 9, 11 plus 9, 20 plus 7, 27 plus 5 plus 3 plus 1. And you see the pattern. So every row is a sum of odd numbers descending. So I call this reverse odd sums. Reverse odd sums. And every time that you add the odd numbers, you get a square number. When you add the first n odd numbers, you get the nth perfect square. And if you add them backwards, it actually creates an incredibly amazing addition practice problem. So I'm a nerd, dude. I'm a nerd. So I actually write it. I don't write it in the triangle method, in the triangular kind of shape. I just write it like this in my notebook. Sometimes I'll underline the way that the numbers are here. I'll underline the last odd that I started so I can, remember, like, where was I again as I was working it. But yeah, dude, just like in a lot of my other videos, 5-minute timer. This thing is so good to try to do 2 and 3 digit additions and get sharper and faster at 2 and 3 digit additions. Oh my gosh, this one is tough. It's really, really fun. Like, I'm finding it very, very addictive. On stream today, I got my new score, my new record from stream today was 13 and 6/14. So that means that I completed 13 squared and I got 6 out of 14 squared. So we can see in particular, 13 squared is 169 right there. And then I got 1, 2, 3, 4, 5, 6 on the next row. So I'm tracking all my records as a fraction like this. I've never done that before, but I'm tracking these. I'm doing these 3 times a day at this point or something, 2-3 times a day. I'm going from 12 and 2/13. Earlier on stream, I got 13 and 6/14, and then earlier today, after stream today, I did another 13 and 6/14, and then I beat that score. Now I'm at 13 and 10/14. I wonder if anybody in the comment section can beat this. I'm not that fast. Definitely other people I know in my life are faster at addition. I'm not the fastest ever at all. I'm sure somebody out there is going to get to 14 or 15 in a 5-minute timer. It's a great exercise. I really do. Another way that you can practice this one is like just keep going. Just keep going until you make an error. So no 5-minute timer, just keep going and you can check your own work. Like, what's so cool about this as an exercise is that you can build all of these meaningful arithmetic addition problems to practice addition. And then at the end of every row, you can check, is that a square number? And in this case, I kept going and then I ended at 246. And I was like, oh no, I missed a 10 somewhere, because that one should have ended at 256 instead. So that's just another way that you can practice this. Like, just keep going, and it starts getting harder. It really does. Yeah, it's a fun one. You can start from any number. You don't have to start from 1. You could immediately shortcut and start at 31. 31 plus 29 plus 27, yada, yada. Okay, cool. So I said that this was a new number sequence, and that is a bold claim. But I'll explain what I mean by that. It really is true. This is my first meaningful mathematical discovery in my entire life. Like, I'm actually incredibly proud of finding this one. And I thought that I was going to get to claim some credit, like post a paper in the archive or something, or post to this, really in particular. I thought I was going to get to post to this website. But unfortunately, dude, I already said it earlier, so I'll just go ahead and jump to it right now. Look at this guy, Rayhan Ahmed, on June 8th, 2026. Today is August 3rd, 2026. So less than 4 months ago is when somebody finally commented and interpreted this number sequence in this fashion. So he noted just 4 months ago, consecutive differences within a row are the first n odd numbers in reverse order. So dude, that is so cool. Like, I thought I was going to get an entry on this wonderful website. It's like a Google search. You can just put in a number sequence and then see if that number sequence means something. Is it mathematically interesting? So going back to 2007, we have like some kind of number theory perspectives on it. Somebody noted that this has a Goldbach conjecture style statement about this sequence. Somebody else noted something about Dynkin diagram weights. So that's crazy to me because I don't even know what this is at all. But people in stream told me today that this relates to Lie theory, which is incredibly cool. All I know is that is like infinite dimensional smooth symmetry groups. So this connects to some like serious research level math. Like, people are noting like much deeper mathematical properties about this same exact sequence. And I just think of it as an addition practice game. And it really is a fun addition practice game. So if I put an entry, I would just say reverse odd sums addition practice. Like, it's such a cool sequence to me. I love this one right now. So there's that. And now to move into the final part of this video, I discovered this sequence, but one of the most amazing things I think right now about this is that all I did was just twist an existing very standard exercise. Like, this is a very, very standard exercise. It's problem 16.1.1 in Lang. It is problem 1.1.5 in Andrews. It's problem 6.1.4 from Velleman. It's just that the way that I'm interpreting it and using it as an addition practice method, like I'm just twisting this very standard exercise into something that creates a fun puzzle, like a fun number puzzle, and something that you can just make you really good at adding numbers in your head. All right, so now we are going to prove the most valuable thing about this math fact, which is that you can check your work at the end of every row. You can check your work. The sum of the n odd numbers is n squared. Like, 1 plus 3 is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 9 plus 7 is 16. 1 plus ... 8. Oh, wait, no. 1 ... 9 is 25. So, how do we prove something like this? How do we know that that pattern will always work? How can I be confident in my error checking method in that square fact at the end of every row? When you have an identity like this, which is a claim or an identity, something that depends on a number n, one of the first things I think of is induction, mathematical induction. So if you haven't seen my video about this from episode 7, go check that out if you want a deeper explanation. But we can go ahead and just jump into the basic strategy here. So what is the strategy for a proof by induction? We need to show two steps. They're in yellow on this proof outline. We need to show the base case and the inductive step. So two main parts to a proof by induction. And so this first paragraph, I'm just iterating. We show that the claim is true for n equals 1. So if the claim is true for the first number, that's called the base case. And then secondly, when it's true for a number, then it's also true for the next number as well. So if the claim is true for 1, then it's also true for 2, then it's also true for 3. Every domino knocks over the next domino, and this identity will be true for every single number. Okay, so to show the base case, we check it for n equals 1. So we literally replace what is the left-hand side when n is 1. There's only one number in that list. It's just 1. And then the right-hand side, if you substitute 1, is just 1 squared. Is it true that 1 equals 1 squared? Yes, of course. 1 is 1 squared, so the base case is true. As I said in the last video, proving the base case is obvious, or sorry, it's not obvious. It's often easy. It's often very easy, and some authors will say that it's obvious, which is super rude, and it's not obvious, but it's often easier than the inductive step. That's the easier part usually. Then to complete the inductive step, blank the blank for blank. Assume the claim for n. So we assume that this is true for n numbers. It's at least true for one of them. So for some number of dominoes fall over, and then we want to say when, is the next domino or is the next case automatically going to be implied from the previous one always? So we assume it's true for n, then we want to show that the claim is true for n plus 1. So assume the claim is true for n, then let's substitute n plus 1 into the left-hand side. Now we have these odd numbers. And of course, it goes without saying, please pause the video and try this yourself at any point to try to complete this. All right, then I can use associativity to group parentheses on the, if I highlight in yellow, maybe the change, we have parentheses around the first n terms there, and then over on the right, we did a distributivity. So I distributed 2 times n plus 2 minus 1 is 2n plus 1. Okay, now this next step is a key step. The left part, that first parentheses, is now n squared by the inductive hypothesis. So we assume that the sum of the first n odd numbers is n squared by the inductive hypothesis, and then we add 2n plus 1. And now look at this. This beautifully, perfectly factors. This is that square of a sum identity from Lang. So yeah, this is exactly the right-hand side for n plus 1. So you replace n with n plus 1 quantity squared. So therefore, the claim is also true for n plus 1. And we're done. We get to draw the cute little square. Thank you, everybody, for watching. I hope you enjoyed this. We've got a couple of exercises. I don't know why I have hidden this one a few times and it keeps coming back. Oh well. All right, so I've got a couple exercises for people who want some more practice with induction. The first one, this is another very standard one. The sum of squares is this identity. Just so you know, I memorize this one personally slightly differently. I have this one memorized, but I have it memorized like this instead. Because then the first term is a triangular number, like the sum of 1 to n. That's the good old formula that we learned from Gauss and from our previous induction lecture. And then multiplied by the next odd number divided by 3 or something. Or, yeah, the n plus 1th odd number divided by 3. That's kind of a mouthful, but I just have this memorized a bit more easily than the former. Anyways, if you want a term for this, these are called the square pyramid numbers, and you can think about why that might be the case. Next, we have another exercise. This one is excellent to work for induction as well. The sum of cubes is the same as the sum of numbers squared. So, dude, this one is so awesome. I actually worked this one last year, coincidentally, on an airplane on the way back home after the holidays. And my friend texted me and was like, hey, did you know this interesting fact about 2025? And I was like, dude, I just solved this. I just worked this exercise for induction on the plane. And I texted him a photo of my handwritten notes. So the sum of n cubes is the sum of numbers squared. And last year, 2025 was this identity when n is 9. It's incredible. It's just a really nice one. So you can prove both of these exercises with induction, or maybe even better, you can do the same exact process as this practice method. You can do the exact same process for these identities as well, and you can add them in forward directions, or it makes it much harder. It makes it so much harder if you add in reverse directions, like n squared plus n minus 1 squared plus n minus 2 squared. It's tougher. I mean, these would be tougher to do, but I think that you could learn it. Yeah, thank you. Thank you everyone for watching. It's a pleasure to share this video and this mathematical discovery that I made. Yeah, I'm proud of it. It's nothing groundbreaking, but it's something. I found something that I can, at least for myself, say that I discovered independently, and it's really fun. It's just really fun. It's better than the Fibonacci numbers, I think, for addition practice, because you just stay in the 2-3 digit numbers for a long time. It's really neat, I think. All right. Thank you all so much. Thank you for watching. Thank you for being here. Thank you for liking, subscribing, all of those things. If you want to share these videos with anybody, mathcanbeahobby.com. It's a way to get to the playlist for yourself if you want to go back and watch the older episodes. There should be a video popping up on screen any moment now. There's also the Discord. It's a really nice, chill community of classical guitar and math fans. And as I always say, feedback is really a gift. Let me know what you like and what you don't like about these videos. What could I do better? As well as what do you like the most, so that I know what to do more of and what to do less of, right? Thanks. All right, and now special thanks to all of the super channel regulars. Yeah, all the people helping teach me advanced math live, and some of the students who I'm working with on the weekends. And to all the channel members, dude, this would not be possible without all of you. we've got, since last time, Lords Marie Walker, Jess Sullivan, and Amelia Garbo. Thank you all for becoming hobbyists. And now we got a bunch of people. We've got a bunch of Luna members, and special shout outs to Eagle Rider and Chakravar. Thank you. Dude, thank you all so much for joining. Yeah, I thought that there were more, but maybe not. I think that that's it. Thanks for watching, everybody. Take care. Bye. I'm sorry Luna didn't show up. She was really acting up earlier, so I'm surprised that she didn't hop up today, but maybe next time. One last thing, live streams are now splitting to a new channel. So if you are a fan of the live streams, please do subscribe to new channel, Practicing Math Live. So live streams are now going to be on a separated channel. This is the #1 piece of feedback I've gotten from a lot of people. It's that they're confused about the live streams. They like these videos, but they don't like the 5-hour live streams, or they're confused by those. They think my course is very disorganized and things. It's like, no, that's not the course. Like, don't watch those. I don't recommend you watch these videos, but if you like them, who am I to say? I don't know. If I'm live, come by and say hi, and let's chat. Let's chat math sometime if I'm live. But yeah. Practicing Math Live, brand new YouTube channel. Hope you check it out. Thanks for watching. Bye, everyone. Bye.